So we're going to be looking at Newton's laws of motions today. Newton's first law of motion is that an object will remain at rest or in uniform motion unless acted on by an external force. Here, the car continues in the same direction because there's no friction or external force to prevent its onward motion. Newton's second law of motion is that the acceleration of an object, as produced by a resultant force, is directly proportional to the magnitude of the resultant force and in the same direction, and it's inversely proportional to the mass of the object. Or put more simply, F, which is the resultant force, equals the mass times the acceleration. So force in newtons, mass in kilograms, acceleration in meters per second squared. The force produced by the car there, by the car's engine, is much smaller than that produced by the steam train. Yet because the steam train's mass is so much greater, the acceleration of the steam train is significantly slower than the acceleration in the car. Weight is a special but important case of Newton's second law. So weight in newtons is equal to mass in kilograms times acceleration due to gravity, which we take to be 9.8 meters per second. So weight equals mass times gravity. So here is a picture of someone. If they have a mass of 80 kilograms and they're on Earth, where we take gravity to be 9.8 meters per second squared, then their weight is 80 g newtons. Newton's third law of motion is probably the most famous one, that for every action there's an equal and opposite reaction. So here is my mechanics book on the table. As you can see, it still has its weight, mass times gravity, but the reaction from the table is stopping it from moving, so it's keeping it at rest. Okay, we're going to do a couple of straightforward examples now. So here, the acceleration due to the force P on our particle here is 3 meters per second squared. That means that the resultant force, which is P minus 10g, so because we're going to take the acceleration to be positive, we're going to have P in the positive direction and 10g in the negative direction, is equal to the mass of the object, which is 10 kilograms, times the acceleration, which is 3. So we know that P minus 10g equals 30. Then we can rearrange that, so P equals 30 plus 98, which equals 128 newtons. So using Newton's second law, F equals ma, we've been able to work out the size of the force P. Another example, this time acceleration is in the downwards direction, so we'll take 10g to be positive, and we know that 10g take away this force P is equal to mass times acceleration. So 10g take away P equals 3, that's the acceleration, times the mass, which is 10 kilograms. So we know that 10g take away 30 equals P. So P equals 98 take away 30, which equals 68 newtons. Okay, final example here. That is, we know that there's no acceleration in the vertical direction because it's not drawn on the diagram. So we know then immediately that the acceleration is 0. So the resultant force must also be 0. So we know that P take away 10g, or equivalently 10g take away P, equals 0. So P equals 10g, which is 98 newtons. We could just leave it as 10g newtons. We also know that there's no force acting in the opposite direction to Q, so we know that Q is equal to 10 kilograms, which is the mass, times 3 meters per second, which equals 30 newtons.